Dr. Ben Grassian is a postdoctoral investigator at the Woods Hole Oceanographic Institution, working with Dr. Heidi Sosek and Andon Lavery on the Ocean Twilight Zone project. He has a Bachelor's of Science from the University of Miami, Rosen Steele School of Marine and Atmospheric Science. He received his PhD from the University of Rhode Island in 2022 as part of the Dr. Creed Roman's lab. And I hope you guys enjoy his presentation.
Yeah, thanks so much. I'm glad to be here. So I'm Ben Grassian, and today I'm going to talk about some of my work using acoustic and imaging systems to characterize animal distributions in the Pelagic Ocean. And so just to begin with some broad motivation, why do I care about the Pelagic Ocean? Well, it's the largest habitable space on Earth, and it's home to the largest population of vertebrates on Earth. So it's enormous, and it's also complex, and it's really undersampled. And so when I'm talking about the Pelagic Ocean, I'm talking about the entire water column offshore. And so to define it, because light is so important for structuring this environment, we separate it into the epi and mesopelagic in the upper 1000. And that in the epipelagic, we have enough light for photosynthesis, and below that, there's enough light to set up these daily rhythms for these animals, but there's not enough light for photosynthesis. And so just to describe some key aspects to characterizing animal distributions in this environment, well, there's this idea that the ocean is patchy, right? That it's not just this homogeneous soup of animals all mixed together. So I really like this image of these pairs of spinner dolphins schooling these forage fish, because you can see the extreme scales of patchiness. Oops. And another thing in this environment is, again, it's not this homogeneous soup, and there's a lot of structure in the hydrography of the environment. So a lot of key features that are of interest to me are things like clines, where we have sharp changes in a physical property. Fronts, like you can see in this illustration here, where two water masses meet, often act as an aggregating device. And eddies, which is this gyre-like circulation that also can aggregate animals in the water column. And so another important component to understanding life in the Pelagic Ocean is this idea that there's this enormous migration of animals every day. So a large amount of the animals present in the water column are undergoing these diurnal vertical migrations. So you can see them really well with the acoustics. So here you're looking at an acoustic echogram, where you can see that at night, all these animals are coming up from depth to feed at the surface, where there's less risk from visual predators. And overall, why am I interested in these sensor-based, these imaging and acoustic-based sampling approaches? Well, compared to the normal way that the traditional way that you sample animals in the water column with nets to collect a sufficient sample volume, you're really integrating this biological information over really relatively large scales in space and time. And you can compare that to our ability to collect these physical measurements like temperature and salinity. And so with imaging and acoustic technologies, we really are able to collect biological measurements at the scales that we can collect the environmental data. And also at the scales to which there is this hydrographic variability to which these animals are responding. And also with things like imaging, we can start to look at things like in situ behavior and this idea of patchiness, like really getting at the finer scale structure of the water column. And so I'd say that my work has been kind of steered by this idea that there's this robot revolution in the ocean, and that the increasingly sophisticated use of imaging and acoustic technologies is really opening up a lot of new insights into life in the water column, which is really challenging, right? You're sampling in a huge 3D space. You're not at an interface. So a lot of my work, the work I'll be showing today, is using towed vehicles and shipboard sensors. And so I organized this talk to kind of show three different studies. The first two I worked on in URI for my PhD with Chris Roman. And the last one is what I'm working on here at HUI. So to kick things off, my first study, we used a deep profiling stereo camera and shipboard acoustics to examine this really intense thin layer aggregation of the squat lobster, Pleuroncodes planipes. And so this was work we did in the Eastern Pacific offshore Baja California. And so this is an oxygen minimum zone environment. So you can see an example oxygen profile where in the ocean interior at this OMZ core between 2 and 600, oxygen's almost down to 0. So this really exerts a strong structuring force on the animals in this environment. And so a lot of the work I did was using the stereo camera profiling system we built, which is basically just a big aluminum frame with 2 cameras facing outwards, like big ROV cameras, and an active strobing light. So we can use this to profile the water column, and it's towable. So most of the work for this project was really in the software side. So it's really taking all this imagery and converting it to meaningful biological measurements. And you'll see throughout my talk, all my imaging work, that's a lot of the focus, right? Like it's very easy for our eyes to say there are crabs in this image. It's very hard to enumerate them algorithmically. So just briefly, the processing pipeline for all this raw stereo imagery we're collecting, we start with these raw data that's affected by 2 sources of lighting variability. So you have a light field that's relatively fixed from the strobe. And then as we're profiling through the euphotic zone, we also have a second kind of ambient photic conditions. So we have a way to estimate those 2 light fields and subtract them out. And you can see in image 2, we're left with a flat zero value background. And so this aids in kind of the classic computer vision problem, which is image segmentation or discretizing all the salient objects in this in the field of view, i.e. the animals. So it's to be able to identify and enumerate them. And so once we have that solution, we have the stereo camera system. So to get 3D, we need to match the features between these 2 regions of interest. And once we have that, then we have, using the stereo camera calibration, we can then know the size of these animals and reproject them into 3D. So this work, that pipeline just spits out a huge amount of this, these paired stereo regions of interest. And so for this project, we were really focused on the squat lobsters. So what I did is I just spent a couple months manually identifying all the crabs. So all this work was to create, to get the crab classifications and their abundance just from manually. And so to provide some sense of the imagery coming from this, you can see on the upper panel, that's a lot of instances of these Chlorincodes planipes after all this image processing. So they're kind of blown out to make it easier for the segmentation problem. And you can see we have scale bars from the stereo camera, so we can kind of assign some real world size to them. And you can compare that to the other members of the community here, mostly gelatinous taxa. And the crabs scatter like really well, really good case study for us, and we can readily identify them. And another reason Chlorincodes planipes is a really good target species for this work is they're just enormously abundant in the Eastern Pacific. So they're often called tuna crab because they're such an important prey item for top predators. And they have both these benthic and pelagic phases, but kind of the transition between them and overall their pelagic habits are just not really well described. And they're also really metabolically adapted for these low oxygen environments. So they're well suited to these OMZ regions. And so before I show you kind of the results of this work, just to provide kind of a qualitative view of this crab thin layer that I'll be talking about. So here's a processed stereo pair image. So the camera A is on the left, camera B is on the right, and then all those crabs or objects have a bounding box, right? So they're discretized. And then they're matched using key points to the view of that animal in the other screen. And so you can see what it looks like to go through this thin layer. So just like 1 meter down, you can see it's just the sharp interface and they're totally gone. And in addition to the imaging, we also had concurrent shipboard acoustics. So RV Sikuliak has a 5-channel EK60. So we had multiple frequencies to work with. And this was pinging concurrent to the deployment of the stereo camera system, which ended up being really useful for textualizing this data. So to begin with my results, here I'm showing an echogram from the shipboard system. down to 400 meters and about 11 hours on the x-axis. And so colors, backscattering strength, how much biological scattering there is. And then overlaid on that in those white lines is the profile path of our stereo camera. So we basically had 2 deployments for this, this day that I'm focusing on. One at midday where we kind of park at that crab thin layer for maybe like 5-10 minutes and keep descending. And then we have this repeat profiling where we're sending our stereo camera up and down that covers this day-night transition. And so a really cool thing about combining the imaging and the acoustics is from the acoustics, you can see this high intensity, really vertically compressed feature, but I don't know what comprises that layer, right? But from the imagery, it's very easy to know that that's the crabs. And so here I'm showing the acoustic data, but now I'm overlaying in bubble plots the abundance from our stereo camera. And so this is the average abundance of those crabs in our imaging volume, which is about 8 cubic meters. So 2 things to point out. So during the midday profile, you can see that the crabs are reaching about 80 individuals per that imaging volume, which is 2 to 3 times higher than we saw later. So they're really most compacted. That thin layer is most intense during that midday. And during that day-night transition, you can see that they're maintaining that thin layer. And there's this sudden kind of rapid loss of the thin layer. And some go surfaceward, it appears, and then they start descending back down. And so it's interesting to note from the acoustics. So, you know, when I first worked up all the stereo data, you know, it took so long and we finally have our results. It's very hard to contextualize what was going on. And the acoustics really brought out some important aspects, right? So you can see that there's the shallow migrating layer that's coming up and ascending through the crab thin layer. And the crab thin layer is just totally happy. It's maintained. You know, they're not responding to the arrival timing of that layer. It looks like the dispersal or like the loss of this thin layer corresponds to the exact moment that this midwater mesopelagic layer comes up and ascends through that scattering layer. So you can see how the acoustics really help contextualize this moment in time where the thin layer is, all these crabs are just migrating surfaceward. And you can see here, I think this is the major mesopelagic layer was between 400 and 600 meters. You can see that response is coincides with the timing of the thin layer dispersal. And then also with the acoustics, you can see that it appears that they're reforming a compact aggregation around the same settling depth that they had that thin layer. So the acoustics added a lot for us. And so, you know, we also have all the environmental sensors with the camera. And so I wanted to kind of beat out what were some correlations between this thin layer that's maintained and the environment. So here, just simply, you can see chlorophyll data overlaid on the survey path of the stereo camera. You can see that the chlorophyll max corresponds to that shallower scattering layer, and also it corresponds to a secondary peak in the crab abundance. And so they're kind of sitting at a layer below the chlorophyll max. And when looking at the environmental data, what really ended up standing out as helping to understand the story of these crabs was when we looked at buoyancy frequency, a measure of the water column stratification. So here what I'm showing is buoyancy frequency for every profile for that repeat profiling. So every one of those profiles is parsed out. And I'm plotting now the abundance on the buoyancy frequency profile. And you can see that the max crab abundance is now I'm plotting on density space. And you can see that at the 1026 isopycnol, this is where that crab thin layer is parked. And so in pressure space, you see this oscillation. And in density space, they're tracking this isopycnol. So they're sitting on this high frequency internal wave. Another really interesting thing with this is you can see that the maximum crab abundance, this thin layer occurrence, is sitting on top of a local peak in buoyancy frequency. And so buoyancy frequency, you can think of it like the density gradient, right? And so there may be some desirability to sitting on what's essentially a density shelf, right? Like if you're not positively buoyant, it may help you. So that was kind of interesting and suggested those aspects to me. Another interesting thing is you can see I highlighted these last profiles. So this is where the crab thin layer was occurring and then all of a sudden it was gone, right? And what's happening in the water column at that moment is you're having all this, that mesopelagic scattering layer ascending through to the surface, and you're also having now the crabs migrating up. And you can see that it looks like the finer scale structure of the buoyancy frequency profile is kind of smoothed out, right? Which would be evidence of mixing potentially. And so this was kind of really intriguing to me, and it's kind of really controversial to talk about biogenic mixing, depending on who you're talking to. But we tried a lot of different smoothers, and consistently we'd see this loss of the high frequency content that's occurring with the migration. So that was neat. And to take that one step further, I also wanted to look at, does the intensity of the stratification relate to how abundant that thin layer was? And so what I'm looking at now is only profiles where the maximum occurrence of those crabs met the thin layer criteria. And so all the ones where the thin layer's gone and other ones where we don't have them, we're not looking at that. And what I'm looking at is the maximum abundance of these crabs on these profiles versus the stratification at that depth that we found their max abundance. And so you can see that it does appear that there's some relation where higher stratification at that depth that they're sitting on relates to a higher crab density. It's kind of suggesting again that idea of like this allowing for the compaction of these crabs on this density show. And then lastly, I kind of, I mentioned, with imagery, we can start looking at animal behavior. So I wanted to start doing that too with this data. And also from the acoustics, those migrating layers coming through are kind of a really interesting part of this story. So if we could glean from the acoustics some understanding of the composition of these scattering layers. And so to get at the behavioral part, I made a really simple proxy for describing the escape response for these squat lobsters. So when these squat lobsters are really rapidly moving vertically, they'll do this escape response where they slap their abdomen shut. And so all the ones on the left, you can see are all kind of flying upwards. And so just using the aspect ratio of the bounding box, that's a really easy way to threshold out all these migrating individuals, these ones that are postured in this escape response, versus these ones where their pleopods are outstretched, they're kind of in this buoyant, senescent posture. And so using a threshold in aspect ratio to assign these migrators, I can look at the fraction of them that are these swimming individuals. And so you can see at that midday observation where the thin layer is most intense, it doesn't appear like many or any above are in this migrating posture. And that is the same throughout most of the day. You can see that there appears to be more swimmers upon the arrival of that early migrating layer. And then upon the arrival of this major mesopelagic layer and the movement of that thin layer upwards, we're reaching about 60 to 80% of the animals in that migratory posture. So it's nice to see the simple matchup between what we're seeing distributionally and seeing it directly with evidence of an escape response behavior. And then on the descent downwards, it looks like most of them this is a much slower descent back down than it is for their ascent. So it seems like they're readopting that kind of outstretched posture. And then in a really kind of crude attempt with the acoustics to glean some information on the identity of the scattering layers, I just looked at the frequency response difference between scattering at 120 kilohertz, so a higher frequency, and 38 kilohertz. So in a really crude sense, you could think of your different acoustic frequencies as different mesh sizes, and kind of ignoring swim bladders and resonance. For the most part, you can see that things that like a copepod would not scatter at these big wavelengths at 38 kilohertz. So they'd have much higher scattering at the higher frequency. And so to look at that frequency response to differentiate between zooplankton that would scatter at higher frequencies versus fish that would kind of have a zero-centered response. So if you look at that early migrating layer to which the crabs aren't responding, it looks like they're having a much more positive, much higher response at the higher frequencies. And so they're likely zooplankton, whereas this layer has a zero-centered response, which is indicative that they're likely fish. And so in summary, this project, we really were able to combine the optics and the environmental and acoustic measurements kind of synergistically. So with the image data, we were able to identify all these crabs, enumerate them, and get their distributions in the water column, and also look at things like their behavior. With the acoustic data, we got the context of all these scattering layers in the environment and their migrations, and also were to assign some broad identities to these scattering layers. And this is kind of a novel characterization of an aggregation of micronekton that meets the thin layer criteria. Micronekton are kind of hard to describe, to study. And I think what's really kind of the take-home message for me of this really, short-lived event is the specificity of that response to a specific migrating layer in their dispersal response. And, it really speaks to this growing understanding of all these behaviorally mediated components of these rapid changes in the distribution of animals that are happening at these crepuscular hours. And so I think it really speaks to kind of that component of these short-lived windows at day and night, where there's all these interactions happening between these animals. And so to switch gears, also for my PhD, I worked with a high-resolution toad profiler that was built in the Roman lab, and we equipped it with a broadband fisheries echosounder. And so kind of to highlight the utility of this asset, I want to compare it to regular shipboard echosounding, so kind of the most standard way to use acoustics for a pelagic survey. And so on the left, you can see an echogram from RV Falkers, downward looking 200 kilohertz. So you're looking 0 to 500 meters on the y-axis. And in the upper 200 meters about, you can see these coherent filamentous features. Those are the biological layers. These are real scattering layers. These are where the animals are. Below about 200 meters, you see this kind of rainbow ramp up of color. That's just noise, right? So you're not getting any good signal below the upper 200 meters from the system. Another important thing to note is that you're really only collecting environmental measurements at the surface where the ship is steaming. And so you're missing kind of all the hydrographic context for all these scattering features that you're resolving acoustically. And so the Wireflyer is a two-bodied system pictured on the left. And it consists basically of a giant 2,100 pound weight that's fixed to the end of the ship's tow cable. And so we pay that out and it keeps the ship's cable taut. And what this does is it allows for the Wireflyer to literally roll up and down the ship's cable using the lift created by wing foils. And what this does is it decouples the vehicle motion of the Wireflyer from the tow cable dynamics. And it allows for us to achieve these really dense horizontal repeats. So we're getting, a repeat profile in about every 600 meters about, which is really kind of novel to be able to resolve that oceanographic section at those horizontal scales. And we can kind of communicate with the Wireflyer through acoustic modem between the clump and the flyer to prescribe missions on the fly and kind of get real-time updates. And so a really unique and kind of unusual aspect to our integration of the acoustics was we have a Simrad EK80, but we have our transducers looking sideways, which is very atypical. Usually you're looking upwards or downwards using these echosounders. And one reason we decided to do that was because the insonified sample volume is orthogonal to our survey path. And so we're getting this 3D ribbon of data as we're undulating through the water column. Also, our acoustic measurements and our biological measurements from the acoustics are really co-located with our environmental measurements, right? So like, as we're pinging down below, we're looking at kind of the same physical and biological environment as match. And we're also conserving the beam geometry across the vertical sampling distance, right? So we're not locked into the surface our beam isn't always huge at depth. And it's kind of a really neat way to be able to source high frequency acoustics at depths. And we have a 70 and 200 kilohertz, and we trigger those separately on up and downcast for like hardware reasons. And so before I kind of show you again the pretty pictures, the results, I just want to talk about some of the nuance of looking sideways and the fate of a side-looking ping at a scattering layer. And so, for kind of first order, most of these scattering layers in the ocean are largely vertically compressed and horizontally distributed, right? So from the shipboard perspective, looking down, the high backscatter return really occupies only a small part of your sample range. Whereas from the side-looking perspective, when you're looking across that scattering layer, you're getting a high-intensity backscatter return across the entire sampling range, which not often happens from the downward-looking perspective. But in both cases, you have these signal loss, right? The sonar equation. So you have your signal loss terms accruing over the sampling range. So, the geometric spreading of sound in seawater, the chemical absorption of sound in seawater, and all the scattering that's not directed back at the transceiver, we're accruing these losses of our signals over the sample range. And so from this horizontal perspective at the scattering layer, what you can see happen is you have relatively constant backscattering, but again, you have that logarithmic loss of your signal. And so you basically just have a signal that's attenuated over the sample range until you hit the noise floor. And, usually when you're getting the derived quantities we care about, like scattering volume and target strength, what we do is we can estimate our loss terms and add them back, right? So that's through what's called a time varying gain function. And what that does, though, is you're no longer looking at the data with respect to a fixed noise floor. And so not to get into all the details of why we did this, and maybe we shouldn't have done this, but the following 3D plots, we're treating the data, the scattering volume data, with respect to a fixed noise floor. So we're kind of taking out that trend. And so to orient you on kind of the raw data that we get from this side-looking wireflyer system, so here's the full 3D data from the system. And so that axis going into the page is our 0 to 100 meter thwartship range. We're undulating from the surface to about 300 meters on the y-axis. And we have about 5 profiles and 2 kilometers. And so you can see these high intensity scattering returns here and below. These correspond to the scattering layers, and you can see some individual targets resolved across range and across pings. And so that's just a small subset of a typical data set we get from a deployment. So here's just in a 13-hour deployment, over the night, we're getting, I think like 100 of these profiles. Like it's really dense, but you can see the full 3D data set here. And so again, a lot of the work here was in getting software just to look at the data, which I think a lot of can be a whole project in of itself. And then, this vehicle-borne data has a lot of nuance, right? There's a lot of sources of noise. And so a lot of work went into characterizing our noise sources. For instance, our modem is stomping on us, and we also get surface reflected ping. So there's some nuance to this data. And so once we kind of are happy with how we're treating our data, I put work into fusing it with all the other sensors and register it to other acoustic data that we collected, and then to develop some visualization methods for this type of data. And so kind of the first big result, and I think kind of the most major result from this vehicle, is just these really detailed concurrent acoustical and environmental sections. So on the left, I'm showing these acoustic sections where now I'm averaging every ping across range to derive mean volume backscattering screening. So I'm basically collapsing that 3D data into a 2D echogram just by averaging across range. So you can see scattering at 70 kilohertz here for a section, the same section at 200 kilohertz. And then we have our environmental data, right? So you can see temperature, we can see this really intense front and this kind of entrained layer. In oxygen, you can make out the water mass structure in this environment. This data was in the Baltimore Canyon, offshore Maryland. And in chlorophyll, you can see, the chlorophyll layer corresponds quite well to the distribution of the scattering at 200 kilohertz. And so to dive one step further into the results, I want to show you, the wireflyer acoustic data, but in the context of other sensors. So our own environmental sensors and also concurrently collected acoustic data from a shipboard perspective. And so to orient you on this 3D plot, I'm showing you in that grayscale backdrop is a kind of traditional 2D echogram from the shipboard perspective. So we were towing a towfish that had downward looking EK60 system. And so we're looking at 38 kilohertz scattering from the shipboard perspective in that grayscale backdrop. And then we're overlaying that wire flyer, the registered wire flyer data in 3D atop it. So we're looking at scattering at 70 kilohertz on the flyer. So we're not detecting acoustically the same things, but first order, the scattering layer distributions between the flyer and the shipboard perspective match up, which for us was good to know we weren't just looking at noise. And then you can see this diel vertical migration event where this migrant layer becomes empty after this event. Another kind of really interesting DVM event we captured was, this backdrop is from RV Falcor's 200 kilohertz system. And I'm overlaying the 200 kilohertz from the wire flyer. And so what you can see is below about 200 meters from the shipboard perspective, we're no longer tracking that scattering layer, right? Like our signal's attenuated, we're not being able to track these scattering layers as they're going deeper. With the wire flyer being, sourcing our acoustics at depth, we can continue tracking this acoustic scattering layer. Another kind of really neat thing here is you can see this last descending layer appears really kind of episodically or patchily in the 2D echogram. And in the wire flyer perspective, we actually can constrain these as athwartship patches. So we're not only looking at patches in the horizontal, we're looking at it at that additional horizontal dimension. So it's really neat to be able to directly measure these patches that are this last descending layer. And I actually think there was a lot of evidence in this data set that this layer was being preyed upon by marine mammals. And so another kind of good example of the difference between the shipboard perspective and the wire flyer perspective. So here I'm showing 38 kilohertz shipboard data at a cold sea plume. And so you can see the seafloor here, right? And then you see this muted plume. And then with the side looking perspective from the wire flyer data, you can see how much more detail we're looking at this cold sea plume with. So we're really constraining this plume across its athwartship structure. And it looks like we have some kind of information on the point source information for where it's coming out of the seafloor. So you can just see how much more detail we're looking at this water column structure with this side looking perspective. And kind of lastly, I think the most valuable aspect of the system is the fact that we're concurrently matched to environmental data. Every biological measurement is within a hydrographic context. And so to show kind of the power of that, here I'm showing again range average scattering from the 70 kilohertz on the wire flyer. So that's our color. So yellow is high scattering. And then I'm overlaying the oxygen contours on top of that from our environmental sensors. And so to situate you here, we're looking in this oxygen minimum zone environment where at 600 meters, we're at the lower oxycline. The oxygen concentration is starting to kick back up. And so you can track this oxycline with these contours, and you can see how tightly coupled the biological distributions are to these fine scale oxygen gradients at these sub-mesoscale distances. And again, the ability just to kind of see that, directly measure that, is really novel. And one more kind of example of the matchup between the environmental data and the acoustic data. So again, here I'm showing range average backscattering in color. So this is our 200 kilohertz now from the flyer. And this is that same front I kind of showed off a little earlier. So you can see I'm overlaying contours of density, oxygen, salinity, and temperature. You can see temperature and salinity really define the front. And you can see how the front really differentiates this area of really high scattering in the front, and then outside of the front, much less scattering. And it seems like there's, an apparent matchup between some of these turbulent features as well, between horizontal patchiness and the scattering there. So that was neat to directly measure. So kind of in summary of this work, we were really fortunate to be able to test this system on a number of oceanographic cruises. So we were able to deploy it in a number of oceanographic settings. And I think, I hope that I've illustrated the utility of this vehicle for, sampling these common scenarios, right? Like fronts and inclines, and to be able to look at the environmental and biological information together, at these really fine resolutions is really powerful. And so we were able to look at, this tight coupling between the environmental data and the biological data, and also start to look at these things like patchiness in the horizontal, which I find really exciting. And so lastly, I want to talk about what I'm working on now at Woods Hole. So I'm working with Heidi Sosek and Andoni Lavery. And so Heidi has this amazing imaging system. It's a shadowgraph imaging system. So you can see here, this is a larvation outside of its house. So that's one of the images from the system. And so the real goal of this project is to take all this. This is an imaging system that's on this tow sled. And so we're profiling up and down just like the wire flyer. And, it has an acquisition rate of like 15 hertz. So there's a huge amount of data. It's probably the most data I've ever worked with. And so the real goal of this project is first, again, to derive all the biological information from these imagery. So what are you? Are you a ctenophore? And how many of you are there? And so to do that, we're doing a machine learning approach. But ultimately, what we want to do is to take all that abundance and biometrics we can derive from the imagery and feed that into forward scattering models to do forward scattering predictions. And so really to say, how do we expect scattering to look based off our image data? And how does that compare or match up to water column scattering measured from a shipboard or vehicle-borne perspective? But I think along the way to that, there's going to be a lot of interesting insights from just working up all this biological data from the imagery. And so again, I just want to highlight the image set I'm working with. And so for these machine learning models, we need to feed it, spoon feed it, all this labeled and classified data. And so I'm starting with these relatively coarse groups covering kind of the major players in the zooplankton community we're seeing at this site. And so I'm starting with, again, these coarse groups. And then another thing to point out, again, is just how drop dead gorgeous these images are. And so the shadowgraph technique really works well. We're capturing a shadow of these images. It's an ordered beam of light, a collimated beam of light, and we're getting the receive on the other end. And so it works really well for the gelatinous taxa that we all, that are often too fragile to be effectively sampled by nets. So yeah, that's something to point out. And so a big part of what I'm working on now and have been working on is creating a model to detect this classic problem of classifying all the animals in these images. And so we're doing a machine learning approach, but we're taking what's called active learning implementation of that. And so what that means is, again, I'm starting with this labeled training data. This really is the onerous part of this project, this labor intensive part. And then we can, once we kind of spoon feed it all these examples, we can derive a model to predict. And so what this active learning approach is using those model predictions. So we'll run prediction on the entire data set and then put it in an environment where users, like poor souls like me, can go and look at all that data and correct it, right? And so what you're doing is you're basically using the predictions to supplement your training data. So every iteration, you're increasing the fidelity and the size of that training data and presenting it adversarial examples, right? So like, you got this wrong, let me tell you again, type deal. And so once we're satisfied with our performance, then we'll just use our model to derive zooplankton abundances. And then we have some pipelines in place to really derive detailed biometrics from the animals. So here is just a really crude attempt at doing a 3D estimation of the shape based off the distance transform of the object from this little copepod. So we're interested in that for the scattering models, really putting in a dense mesh would be interesting. And so just to show you the kind of state of the art of this model right now as I'm working it up in a really qualitative fashion. So here's a smattering of 12 training examples on the left that were labeled by me. And then on the right is the model predictions. So you can see, it thinks this is a radiolarian, which I didn't think it was, but at least this confidence is quite low for that prediction. So these are the kind of things I'm assessing when I'm looking at this. And you can see that another aspect to training a model like this is there's often many different animals in each training frame, and we're actually feeding it based off the whole frame. And so kind of the burden of making the training data is increased a little bit because we have to get every little copepodite in there. And to present kind of how well our model's performing in a more quantitative manner. So on the left, you train this model over these training cycles or epochs, right? And it will asymptote to this is the best estimation I have. And so what you look at is a measure of precision, which is how correct are the classifications, how many are you getting correct? And then recall, which is how many of the total are you actually finding? And so an average, the harmonic mean of that is the diagnostic for these models. It's called an F1 score. So you could think of it like a model score of 1 means the model got everything right, didn't get anything more than it needed or anything less, and everything's classified correctly. So right now, among all the classes, we've increased to about 85% average F1. So this is kind of state of the art already for zooplankton. But you can see that, so now I'm plotting precision and recall against each other. You can see that the model skill isn't the same for every taxa. So we'll have to treat that on a taxa-specific basis to get the highest fidelity predictions. And just to show some preliminary results from working up this data. So you can see that I'm really interested in combining the imaging and the acoustics because I really think they're complementary, right? And so just using a prototypical model, so something I don't really trust too much, but for the copepods, for these large copepods, it was doing pretty well at predicting them. And so getting now the model to give us the abundance for this entire cruise, which was, I think, like 3 days, you could see the abundance from the images, again, overlaid on the shipboard acoustics. And so this is shipboard's 38 kilohertz, so they're not seeing copepods, but you can see that the diel habits of the copepods really seem to match overall the diel habits of the 38 kilohertz. And again, you can see how powerful it is to match these up for looking at the ecosystem structure. And then scattering at 200 kilohertz, where you could feasibly detect these larger copepods near the surface when they're abundant enough. This is just some kind of tantalizing, to me, a matchup where there's this patchiness in scattering at 200 kilohertz that seems to match up to the imagery-derived abundance profile. So this is kind of the type of stuff that once we really get a good model going with all these different taxas, to really, I think that will be a good substrate to look at. And then, some more preliminary just for the copepods. So here I'm just plotting their distributions for just time of day, right? So taking all that profile information and putting it by time of day. You can see it looks like all the copepods here are undergoing diel vertical migration. Not exactly what I would expect, but you can see that we can already kind of resolve their diel habits. And it's likely because that model targeted these large adults, maybe of a specific species. So yeah, that's what I worked out. And so, I've been there that long at Hui, and I really feel like I have this totally unexploited zooplankton data set, right? So once we solve all this onerous machine learning stuff, we can really crack open all these zooplankton information. And so, a big part of the scattering model study will involve also incorporating netto information, but I think there's a lot of other synergistic potential with other sensors on the Ocean Twilight Zone project. So it's kind of what I'm interested in, looking forward to this project. And yeah, with that, I want to thank my advisor at URI, Chris Roman, especially, and my collaborator, Melissa Oman, who really helped me bring the science into my life when I worked in a robotics lab. and Andoni, Lavery, and Heidi at PUI. And thank you for having me.
Everyone, now we're open for questions.
Thank you for your presentation. I have two types of questions. My first question is about, like, for training your model, like, is it like enough? Because like there is a lot of species that the visual interpretation, it's not enough, and you have to do like some work in the lab to do the proper identification of these species. So do you think it's enough? This is my first question. And my second question is like, because you were talking a lot about the layer stratification, and it's really related to the variation of due to climate change, especially the temperature. So as a specialist, what are your expectations on the crab abundance average in the future related to this issue?
That's an interesting question. So for the first question, if you're asking if it's really sufficient to just use the image data alone to make assumptions about getting the correct labels, right? Because it's very orientation dependent, and you may want to do some lab studies. Was that the question?
Yeah, because like for the identification of each species, like there is a lot of characteristic, and it's not like the visual. When we see a species, we can't like directly see it's which species. We have to do like some work in laboratory distinction of the.
Yeah. So yeah, the ability to get to species is kind of opportunistic, right? Like if we know that there's only one type of cestotenophore here, then we know that's the one, pretty much. But so for the most part, for the image work, I say that I'm using these crude categories, ctenophore. There's a lot of morphological diversity in that group. And so what we're really going to do is break this out into essentially morphotypes, right? The visually consistent schema of an animal. So maybe there's some cryptic speciation within that, but the goal of this project is really to get the best ID we can get, but we don't anticipate getting to species levels for most things. And actually something that we really should do, and as I'm working up this data, is for instance with the ctenophores, I also have them labeled as a synipid or a lobate or like families. And so as long as the more morphologically consistent a training category is, the better, right? So if I kept this kind of heterogeneous group of ctenophores across many sizes and many different characteristics, I need a lot more training data for it to do well at that. And so breaking out the problem into kind of speciating it more is important. And I think that's something that we're doing. For the stratification story, like what is it going to look like in a warming world? I actually, once when I showed someone this data, they were like, oh, do you think the crabs migrated because there was no longer a local peak in buoyancy frequency, like they started falling or something? And so I don't really have enough information on a why they were sitting there. I think likely there's an energetic advantage. But I'm not entirely sure, like sensory rise, right? That they're seeking out certain stratified or, what they're seeking out essentially. So, in a warmer world, I expect there's, more stratification at the surface. I think that's going to be more about the physical processes like of mixing in general. But for the crabs, I don't know if it would affect their behavior, but it may affect that, that buoyancy frequency profile that we're looking at.
Liz Wagner has a question online.
Okay, go ahead, please.
Hi, Ben, can you hear me?
Yes, we can.
Excellent. Such a great presentation. The side-looking acoustic data from the wire walkers, really cool. I was wondering, are you doing any, I guess I have two questions. Are you using FM pulses, and are you doing any kind of spectral analysis of that data to try to differentiate between species? And then two, if you are using FM data, do you see any issues with the wide bandwidth and like self noise or like mechanical noise with the wire walker actual movement on the line. I've heard some groups here that use something similar. They're doing, sort of ADCP measurements, but with their 200 kilohertz, they have a lot of problems with noise in the system and trying to do broadband work.
Yeah, that's a good question. So all of our data that we collected was FM. So it's, has a chirp. And so we have frequency content. So right kind of at the end of this work, I so wanted to get scattering volume as a function of frequency. And right at the end, we got it. But the spectral response or the spectral information, when, we'd subset to a scattering layer, et cetera, seemed really to lack trend. And I think it's really noisy. And so I do think, so again, we collected all of our data with the capacity to look at the spectral content. But in general, the Wireflyer, to begin this project, it was really noisy. So there was several iterations of this. So the first data set, you could only see out to like 30 meters, right? It was very noisy. And so the WBT Mini that Simrad makes really requires an input power filter. So to clean up the power going into the bottle. And so once we did that, our data was really cleaned up, but we still one of the reasons what I call detrended the data, which is kind of taking out the TVG curve, but taking out the whole trend of the data, is because, let's see if I can find this, sorry. Or maybe I can't quit out of full screen. There's a whole mess of stuff in here, but if I can find it. So what we saw is over the course of a dive, we go down to 1,000 meters, right? And we're pressure cycling these transducers in a way that they're not intended to be, right? We're going from a 300 meter difference in we're going a meter and a half a second. So, we're really cycling this thing under a lot of pressure. And what we found is certain dives, yeah, so this is, let me see. Is that we have this noise floor that totally transitioned all of a sudden. And we think, it has something to do with this. Piezoelectrics are not piezostatic, so we think, so detrending the data on a profile by profile basis helped remove the effect of this change in our noise floor that was going on. And so, yes, our system is definitely affected by noise. And so I think that's why I took it at this kind of real relativistic, aspect. Where are these scattering layers? And when we looked at the spectral content, I think there's a lot more work that needs to be done for that, right? Even just rotating our coordinates for, a thwart chip is not a thwart chip. The elements on the transducer don't really match for that. So, we need to rotate it too. But yeah.
Oh, that's interesting. Does the Wireflyer, does its position change, in the water column relative to perfectly sort of pointed upwards? I can see how, yeah, that would definitely be an issue. I mean, obviously, you were able to do a lot with your sort of, as you said, relativistic data. So it's very cool. I was just wondering if the spectral analysis was possible, but it might be also side-facing. It complicates all of the scattering models. So yeah, more work to be done there. Very cool.
Yeah. Yeah, I think a big thing for the scattering models is, when you're looking sideways, a fish looking downwards is almost always broadside, right? But you're so dependent on how that fish is oriented at you from the side looking perspective, and no scattering model is caring about that, right? So for that quantitative aspect, this is a whole nother can of worms. And because fish are, have that body shape, it would be better to look at them up or down. You'd be less dependent on their angle.
Yeah, their heading. That makes sense.
Yeah.
Anyone else? That's it. First of all, thank you so much for accepting our invitation. And I hope you guys enjoyed the presentation.